of the electron. So today we're going to talk about Coulombs Law. So a quick review, just to kind of connect some vocabulary. Amber rods were first rubbed with animal fur, and it was known that when you rub the amber rod with an animal fur, they acquired something that attracted light objects to them, like feathers or small pieces of dust or like pepper. So the Greek word for amber is actually electron, and so electricus was the adjective which meant of amber. So when early English natural philosophers like Gilbert used or wanted to reference this stuff that was created, they used the word electron, which is the Greek word for of amber. And if it was flowing, they called it electricity or of amber. So that's kind of the root of the word electron. It just really means amber. Um, so in 1897 or so, the actual carrier of the charge was discovered, and the word electron, following the convention that particles end in on, electron was what was used to refer to the particle, which we now know as the particle, the fundamental particle which orbits the nucleus. So this property that is associated with this effect we call charge, and charge is one of the 7 fundamental quantities in nature. We can't really define it in terms of anything else. We just postulate that it is. So some of the ones we've encountered so far, we know length. You can't really define length. It just is. We measured in meters and mass and time. So it turns out that almost everything we've done so far has been in terms of these 3. So if you say, well, what's acceleration? It is a length divided by a time squared. Or if you ask what is a force, force is a mass times an acceleration. So everything we've done can be expressed in terms of these 3 fundamental quantities. And so now we're going to add a 4th, which is the charge. And there's 2 more. There's temperature in Kelvin, and there's the amount of matter, or the mole. So those are the 6, and then luminosity, which we won't get to, the candela, is the 4th fundamental unit of nature. So these 7 quantities, everything we talk about in nature can be described in terms of these 7. So these are the fundamental ones. Everything else we call a derived unit. Okay, so besides rubbing amber with cat fur or animal fur, you can also rub silk with a glass rod and acquire an opposite charge. And so we've already talked about that. The electroscope is an interesting thing. I'm going to link a video here talking about the electroscope. But basically, the electroscope is a device that has 2 leaves that are made of metal. And when you bring a charge and touch this top thing right here, excess electrons, for example, spread out all over the metal, and these 2 leaves repel each other. So an electroscope is a simple way to detect charge. Anytime there's a charge around, or anytime there's an excess of either positive or negative charges on the center rod, the 2 leaves fly apart. So we'll look a little bit more at that in a later video, but it can be used to detect charge. So Ben Franklin did a lot of experiments with electricity. He deduced there were 2 types of charges, and he chose to call them positive and negative. Could have called them anything he wanted, but he chose positive and negative. And he postulated that positive charges were movable, they were mobile, and negative charges were fixed in the material. And it turns out that was exactly wrong. It's the opposite. But to this day, we still use some of the conventions that he introduced at the time. Again, that will come later, but Benjamin Franklin's the guy. So the law of charges basically states that opposite charges attract, like charges repel. That's been known for a long time. And then there's this thing called a Graaff Generator, which if we ever get back to school, I will get out and show you guys. And I think Mr. Meredith or I showed you in your first year physics course. Basically a mechanical way to separate charges. And you can do all kinds of fun experiments. You basically get an excess positive charge on the dome, and then you can play with things. You can shock yourself. You make human chains and stuff like that. So we'll play with that later. So here's kind of the current picture. What we know is that the positive charges are carried by the proton, and they are locked here in the nucleus. They cannot move. So positive charges are not mobile. The negative charge is carried by the electron, and the electron orbits in this vague cloud-like structure around the nucleus. The protons are very heavy, about 2,000 times heavier than the electron. The fundamental charge on the electron is 1.6 times 10 to the minus 19 coulombs. This was discovered by Robert Millikan at the University of Chicago, who was able to isolate single charges. And then the proton has the exact opposite charge. It's positive 1.6 times 10 to the minus 19 coulombs. So that's a fairly important concept. Um, if the metal or if the material is a conductor, what that means is the electrons in this outer layer, the very outer electrons, in chemistry we call them the valence electrons. Those electrons can hop from one atom to the next. They can conduct charge, and if it's an insulator, that electron is not free to roam. So we call that an insulator. So like wood or rubber or something like that. Polarization is this idea that if I bring I have a neutral sphere, which means there's lots of electrons, but they're all paired up with their positive charges. But if I bring a positively charged rod near it, and so what this means is there's an excess of positive charges, so the net charge is positive on this rod. If I bring it near this dome, all the positive charges, they can't move, but the negative charges over on this side, which can move over to the left side. So on the left side, you have an excess of negative charges, and on the right side, you have an excess of positive charges. You have positive charges whose electrons left them. And so you get a separation of the charges. We call that polarization. Um, and that's one of the phenomena that happens when you have charges near each other. The same thing can happen even in a non-metal, like if you rub a balloon on your head, one side gets an excess charge of positive charges, and you bring that near a neutral wall, even if it's an insulator, the electrons tend to slide over here to the left a little bit and produce a little more force towards the positive charges than is repelling from these because they're a little farther away. So that's polarization. So Franklin's bell, I would demonstrate this for you too. So you're missing a lot here, sorry. But he basically had a clever way to detect the presence of charges. So when a thunderstorm was coming, he ran a wire up the top of his chimney, and he connected it to a bell. And he had another bell here that was connected to the ground, and he had a thin little piece of metal on an insulating rod in between them. So what happened was, as the clouds built up a net positive charge, the ground would get a net negative charge, and this bell would become negatively charged. When that bell is negatively charged, it attracts this little piece of metal until it touches it. And once it touches it, all the positive charges that were on that metal are neutralized by the negative charges which hop on. And now that metal is repelled and it goes to the left. When it gets over here, it uh, discharges its negative charges. Now it's positively charged and it just rotates back and forth. And so it would actually ring when the, the air outside his house was becoming slightly charged. And that's how he knew when to go out and do his experiments. So that's called a Franklin bell. All right, so what about Franklin? It's sort of true that he flew a kite in a thunderstorm. He basically did it with a piece of rope, and then the last 5 feet or so he connected with silk, so he knew enough to not shock himself. And he was pretty careful. He did not try to discover electricity. Electricity we had known about for about 100 years. What he was trying to do is prove that lightning and electrical current were the same thing. So that was kind of the gist of his experiments. But he did fly kites and thunderstorms. So once it was discovered that charges exert forces on each other, the next step was to determine quantitatively, the nature of this force. So how does this force depend on things like a charge on one and charge on the other and the distance between them? And that experiment's very difficult to do. It's very difficult to regulate and measure exactly how much charge is on an object. So we did a simulation. You guys did it for lab. And the short story is you found that the force was proportional to the charge. You got a straight line when you graph force and charge. And you found the force was inversely proportional to the distance between them squared. You found the inverse square law. Um, Coulomb was the first guy who put this all together. So we call it Coulombs Law now. And it's fairly simple to state. The force between any two objects due to the electrical charge is a product of those charges, Q1 times Q2. It's divided by the distance between their centers squared, d squared, so it's an inverse square law. And there's some slope or constant or proportionality, which we call Coulomb's constant. Coulomb's constant for the purposes of AP physics is 8.99 times 10 to the ninth Newton meters squared per Coulomb squared. And since those are the units we're using, for our constant, that just tells us the force is going to be in newtons, distances are in meters, and charges are in coulombs. You can look up the charge that constant in other units and use those, but this is the one we're going to use. The fact that there's an absolute value here just reminds us that this equation, this expression, only tells us the magnitude of the force. It does not tell us the direction. We will have to work out the direction and the geometry of the problem. And so there's some examples coming up for that. So we call this force the electrostatic force, or the Coulombic force, and it's the force that governs all of chemistry. Chemistry doesn't really deal with nuclear forces. They don't really deal with magnetic forces. All of the interactions between atoms had to do with electrostatic forces, which is governed by Coulombs Law. It's an inverse square law, which means that if you make the distance between two charges 3 times bigger, the force will get 9 times smaller. So we've talked about that a lot. Hopefully you're getting the idea. Okay, a couple of example problems to solve before you start off on your own big batch. Suppose you have a small conducting sphere and you have an excess charge of 1 billion electrons. What would the charge on this sphere be? So basically we have to use the fact that every electron has a charge of 1.6 times 10 to the minus 19 coulombs. And we can set that up as a conversion. 1 billion electrons is 1 times 10 to the ninth, and we have 1 times 10 to the ninth electrons times this conversion, 1.6 times 10 to the minus 19 coulombs for every electron. So you multiply that by 1 billion electrons, and you get a charge of negative 1.6 times 10 to the minus 10 coulombs. That is the excess charge on the sphere. Mostly we just say what is the charge, but it's never the total charge because there's a whole bunch of other electrons with protons whose charges are not seen because they are shielded. They pair out and have a neutral charge. We're going to use metric prefixes a lot, so here's a quick reminder. They are on your AP reference sheet, so you don't need to memorize them. The one we use a lot for charges is micro, so 10 to the minus 6. All right, so here's an example. Suppose we have two balloons. They're 15 centimeters apart, and each balloon has a charge of 1.2 microcoulombs. So coulombs are really huge charges. So generally when you scrape a balloon on your head or something, you build up sort of microcoulomb as a charge. So that's why we use that. Here's what we got. Two charges, a distance d apart. We know the distance is 15 centimeters or 0.15 meters. And each charge is 1.2 times 10 to the minus 6 coulombs. So just replace micro here with times 10 to the negative 6 and you'll be good to go. We'll evaluate our expression. Our expression tells us that the force between the balloons is 0.58 newtons when we plug in all our numbers. And so if these are both positive charges, these two balloons repel each other. So if we ask what is the charge on Q2, that will be 0.58 newtons to the right. But if we ask what is the charge on Q1, that'll be 0.58 newtons to the left. So this exact same formula tells us the charge on both of them, but depending on what you're looking at, the direction is different. That's why we have absolute values here. The magnitude is 0.58. The direction depends on the geometry. These are both positive charges, and they are repelling each other. So Q2 is pushed to the right, and Q1 is pushed to the left. Okay, one more. What happens if you have multiple charges? Well, you just got to find the force on each charge from all the other charges and then work out the net force, so using Newton's law. So here's an example. I've got three charges, Q1, Q2, and Q3. I know their magnitudes, and I know their directions. And so we are going to try to find the force on Q3, this guy over here, due to the other two charges. So this is a positive charge, and this is a negative charge. So these two, Q3 and Q2, are going to attract. So there's going to be a force on Q3 to the left. However, Q3 and Q1 are both positive. They're going to repel each other. So there's going to be a force on Q3 to the right due to Q1. And we got to find those two forces. So we're going to start off by finding the force on Q3 due to Q1. Okay? So to do that, we need to know K, Q1, Q3 over D squared. K is a constant, it never changes. We have Q1, we have Q2. We're going to ignore their signs, whether they're positive or negative, because we're taking the absolute value anyway. And then the distance between them is 0.8 meters squared. So when we put that all in, we're going to get 0.056 newtons. And this is the force on 3 due to 1. So that's how we use the subscripts here. This is the force on 3 due to 1. And it is pointing to the right because those are both positive charges, so they repel each other. So there's a force on Q3 to the right. Now, what about the force on Q3 due to Q2? Well, we have a negative charge here and a positive charge here, so they are attracted. We can work out the magnitude of the force by putting in our values of K, Q2, Q3 divided by the distance between them squared. This is a typo. This should be 0.05. When you put that in your calculator, you get 0.288 newtons, and that force is on Q3 to the left. So here's what I end up with. I've got a force on 3 due to 1 to the right, and I found its magnitude. I've got a force on 3 due to 2 to the left, and I found its magnitude. Since the force to the left is greater than the force to the right, the net force on Q3 will be to the left, and I can work it out. It's going to be the force on 3 due to 1, which is positive, minus the force on 3 due to 2, which is negative, and that turns out to be 0.231 newtons. So when you have multiple charges and you're trying to work out what is the force on one of them, you have to take into account the force on that charge from all the others, find those forces, and then add them up using Newton's second law. If you know the net force, you could then, of course, find the acceleration, but that's not a question we're asking right now. Okay, so that's what we're going to do. We're going to solve some problems which involve charges and finding the forces between them. So that's homework 9.1. And so get a start on that, and then the e-learning for Tuesday will be to continue and finish that problem set. So this is kind of a 2-day assignment. Please, please, please get help when you need it. During the school day, I will be on my computer and answering emails within a minute or two. If you are emailing me a question later in the evening, it may take me a little longer to respond. But take a picture of your work, show me what you got so far, and I'll be glad to help you out. If that doesn't work, we'll FaceTime or connect on a video conference, which we can do using Canvas, actually. But we'll figure it out. So make sure you get a jump on these and keep working on these because we're going to go on Wednesday to the next idea. Okay?